Hi, everybody. My name is Sarah Klapoff, and this semester I got to work with Dr. Valerie King, and we looked at alpha stretch probabilistic tree embeddings and their applications in physics. I am doing a combined major in physics and computer science, and throughout my degree, I've been really lucky to get to see some of the work in astronomy that people at UVic are doing. And so I've really enjoyed that. And for this project, I wanted to look at PTE algorithms and then looking at applying those algorithms to some problems in physics and astronomy. So today we're going to kind of give an overview of the problem, give a little background, some context, look at probabilistic tree embedding construction, and then we really took an in-depth look at specifically the 2004 work from Bhaktcharanfal, Rao, and Talwar, also known as the FRT algorithm. And so we're going to look at that algorithm, and then we're going to look at some more recent work, where we're at today, and then finally some applications in physics and astronomy. So why trees? If we have a graph, often with a lot of edges and a lot of information, but we have one specific property that we want to inquire about, we can build a tree representation of that graph that will preserve that property. So for connectivity, that's a spanning forest. For the distance to a fixed source S, that's the shortest path tree with root S. And then for the expected pairwise distance for each node pair, it's probabilistic tree embedding. If we can solve the problem on the tree, it will give us an approximate solution on the graph. So in a little bit more broader terms, this is metric embedding. And so a metric is just a way of defining distances between two objects. A classic example is kind of looking at the taxicab metric versus the Euclidean metric. And so the taxicab metric, you can only go up and down and left and right, and Euclidean, you can go on the diagonal. So in this example, to get from one point to the other on the taxicab metric, you have to go all the way up and all the way over, which is much longer than if you're in the Euclidean metric and you can go straight across. Here, in this case, we're taking a more complex metric, which is the graph, which has many different paths between node pairs, and we're representing it with a simpler metric, which is the tree, which just has one path between any two node pairs. Alpha stretch probabilistic tree embedding gives us an approximate pairwise distance, where alpha is the stretch, and it gives us the idea of how close our approximation is. So in other words, if we want to know the expected distance between two nodes on a graph, we can find the distance on T, on the tree, and we will know that that is the distance within a factor of alpha. And this has a lot of applications, both in computer science and physics. So just a couple of preliminaries. We're going to be looking at a connected weighted graph, G with V and E, and then it's tree embedding T, which has VT and ET. DG of U and V is just the length of the shortest path between U and V on G. So it's just the distance between U and V. The stretch between G and T of U and V is the distance on T divided by the distance on G, and it's always greater than 1. The stretch between a graph and its tree embedding is just the maximum stretch between any node pair in G. And then finally, D is just the diameter of G. But one tree does not preserve all pairwise distances with a good stretch. So we want to create a probability distribution of trees, which is where probabilistic tree embedding comes from. So if we can construct this distribution T over the set of trees Ti, that for each Ti and for all node pairs in G, we have the following things. So number one, the set of nodes on G is a subset of the nodes on T. So you can see here all the nodes here are leaves, and we have some extra nodes here on the tree. The second case is that the distance between any two nodes on T is larger than it is on G. And then the third is that the expected distance on T is less than the distance on G times our stretch factor alpha. In other words, the expected stretch of this tree is less than or equal to alpha. If all of these things are true, then the distribution T is an alpha probabilistic tree embedding. Couple things to note though. The PTE, the probabilistic tree embedding, is the entire distribution. So it's not just one tree, it's the entire distribution. Moreover, an alpha stretch PTE algorithm returns just one tree that is sampled from that distribution. So it doesn't explicitly create the entire distribution, it just gives you one tree that fits it. Ultimately, we want our approximations in T to be as close as possible to G. In other words, we want a small stretch or a small alpha. And the randomized algorithm is what really kind of like gets that to be small. So we're going to look at the embedding of an N cycle as an example. So Rabinovich in 1995 showed that deterministically approximating the N cycle in a tree will give a stretch of omega of N. For each edge removed, there's always going to be a node pair that used to have stretch 1, so it didn't change, and now it has stretch n minus 1. Now it has to go all the way around to find a path connecting those two nodes, which isn't really great. So instead, Bartal in 1996 says, okay, let's randomly choose one edge to delete, and we'll build a PTE, and then he shows that that PTE has a stretch of alpha equals 2. So really quick, I'm just going to go over this pretty quick here in the interest of time. What he did is he said, okay, for each edge in here we can delete it, and that creates a tree. And the stretch of these trees is n minus 1. Then we're going to take the distribution of all of these trees, and each tree has the same probability 1 over n. And then he says, okay, in the event that a edge xy was chosen, the expected distance on T is this here, which is, I'll just explain it really quick. 1 over n is the probability that that edge or that tree was chosen. And then the stretch is n minus 1, and that comes from deleting this edge here. So you have to go all the way around. Plus the probability that it wasn't chosen, which is n minus 1 over n, and then the stretch stays the same as 1. And so from our definition of a PTE, we see that the expected distance for all trees on this distribution is less than 2 times the distance on this cycle. So the lemma is that there exists a 2-stretch PTE for the n cycle Cn. And we can see here that by building a randomized PTE, we're able to lower the stretch significantly. So from omega n to 2, which is pretty good. So looking kind of back at some of the history, Bartal in 96 was the first one to introduce this idea of probabilistic tree embeddings. And then he also showed in 1996 that the lower bound for the expected stretch is omega log n. That means that when FRT showed their algorithm in 2004 that gave this O of log n expected stretch, we knew that it was asymptotically tight, and we can't do any better. So this FRT algorithm, which we're going to talk about more in a second, it has expected stretch of O of log n, but the runtime is still polynomial. And so Mendel-Schwab in 2009 improved that to m log 3n, and then Blalock, Ga, and Sun in 2017 improved that further to m log n. And so that currently is where kind of the state of the art and where we're standing now. But we looked really in depth at the FRT algorithm. So first we're going to look at how they constructed their PTE, and then we're going to look at how they decomposed the graph. So this is their theorem here. They say that for any graph G, there exists a probabilistic tree embedding T with stretch O of log n, such that for all pairs of nodes in G, and for all T's in this, and for all trees in this distribution, that the distance on the tree is larger than the distance on the graph, and that the expected distance on the tree is smaller or equal to O of log n times the distance in the graph. And these points just came from the definition of a PTE, but we can see that the O of log n is where they have their stretch factor. So the idea for their algorithm is, given a graph with a diameter d, we're going to iteratively decompose G into disjoint subgraphs using a randomized procedure that has the following properties. So we're going to talk more, this is the decomposition procedure, and we're going to talk more about this in a second. But the properties are that for all subgroups, in each step, for all subgroups, the diameter of that subgroup is at most d over 2. So at most, it's the diameter of, it's like parent graph divided by 2. And then the second property is that for all node pairs in V, the probability that U and V are assigned to different parts, G of I, is at most the distance in G divided by D times this factor alpha. This figure here is just showing a laminar family, but it's the same procedure as within a graph. So first look at it a little bit more in depth. First we split G into subgraphs, G1 to GL, so there are L subgroups. And then we're introducing an extra node, R, that is not in G. And then we're connecting all of these subgraphs with edges with weight D. So note that at most, the diameter of each subgroup is now D over 2. And the weights here correspond to the diameter of the original graph G. Then we just repeat this procedure iteratively on each subgraph. So we look at G1 and we just do this again. So we decompose G1 into subgroups. We introduce, so these subgroups here, G11 up to G1L1, and we introduce a new root R. We connect all of these subgroups with edges that have weights corresponding to the diameter of G1. So in that case, here we have D over 2 because at most the diameter of G1 is D over 2. And then note here that the diameter of each one of these is at most the diameter of G1 divided by 2. And so we just continue to do that on all of these subgroups and then on all of these subgroups and so on until G has been fully decomposed into single nodes. And so now all of the leaves of T are exactly the nodes of G. In the decomposition procedure, so that's the procedure that splits up, that makes these partitions, these subgroups, the partitioning itself is randomized. And so as a result, T is a random tree that's produced as a part of the distribution. So in the end, you get this tree, and we know that it's a random tree because the decomposition procedure is randomized. So just bringing it back to the two PTE properties, we can prove that this algorithm does indeed produce a correct PTE by proving that these two are satisfied. And I'm just going to explain them like really broadly in the interest of time. So the first property is that for any two nodes, the distance in the tree is larger than the distance in the graph. And this idea, the proof idea, is that any two nodes, U and V, share a common ancestor on some level I. And so what that means is that on this level I, they belong to the same partition, we'll call it G of I, and that partition has some diameter, we'll call it delta. So the distance on G between U and V is at most the diameter of GI for delta. On T, the edges connecting the subgroups containing U and containing V have weights corresponding to the diameter of GI, which is delta. And so to get from U to V, you have to go up the subtree that contains U and then down the subtree that contains V. And through doing that, you have to travel over at least delta and then delta again. So at least you're traveling over two edges of delta, and so the distance in T between U and V is at least 2 delta. Remember, the distance in G is at most delta, so we know that dt is greater or equal to dg uv. For the second property, once again, we look at the event that U and V have their common ancestor at level I, and we use the fact that the diameter of the tree is bound by 4d. And then we also use the second property of the decomposition procedure, which is that the probability that U and V are separated at the ith level is at most dg uv over d times O of log n. And so we can calculate the expected distance on T, and we show that this inequality does hold. And so this is our construction part for the probabilistic tree embeddings. And each one of these subgroups, like I said, is created using a decomposition procedure, which I'm going to talk about now. So this decomposition procedure, like I said, is used to create the subgroups GI in each step of the iterative algorithm. And there are lots of different ways to do this as long as they satisfy those two properties outlined in the algorithm. And so the one that we looked at is as follows. You choose a radius at random on the interval d over 8, d over 4. You choose a random permutation pi of all of the nodes in G. And then we build balls to create the subgroups GI. So a ball, we can use this as an example. B of pi of I and theta is a collection of all of the nodes within radius theta centered around pi of I, where pi of I is a node. And so on the level I, the subgroup GI is created from all of the vertices within a distance theta from the center pi I, which you can also think of as the ith vertex in this permutation. So we have that. Then we subtract all of the balls of radius theta that have a center that came before I in the permutation. And so this gets rid of already assigned vertices. The ith ball is still built even if pi of I is already included because it hasn't been the center of a ball yet. So it might just be a smaller partition. And so this procedure does satisfy these two properties. To kind of put it all together, to summarize the FRT algorithm, we have this graph decomposition procedure, which supports these two properties stated by the FRT algorithm. This FRT algorithm then produces a probabilistic tree embedding for any graph G, and the stretch on that PTE is O of log n, and that on the bound of the stretch is tight. this algorithm does have a polynomial runtime, and it's since been improved, like I said before. So I'm just going to bring this back. So as I mentioned, Blalock and Sun in 2017 improved the runtime of this algorithm. They improved it to O of m log n, which is pretty fast, and it's also the best we have statically right now. And then also currently right now, there's work being done on a dynamic PTE algorithm. So that's when you have a graph that's undergoing insertions and deletions, and you maintain a PTE for that. And that's still very much an open problem. So next, I want to talk about some applications. One of the applications that I looked at was the Biot bulk network design problem. And so a lot of astronomical surveys require processing huge amounts of data before they release it to the public. So for example, I looked at the Rubin Observatory LSST survey, which is a huge survey. It's going to start 2025, and it's going to take 20 terabytes of data per night, every night for 10 years. So it's a lot of information, and it has to be all processed quite quickly. Processing all that is going to be a challenge, but we can modify it as a Biot bulk problem to improve the time it takes to process all of that. So to model the data management of this LSST survey, we're going to modify the Biot bulk network design problem to fit our LSST model. So in the model, we have, we're going to represent the data management as a network of machines that are sending and receiving data in different stages of being processed. And that's our G here. The edges, E, are going to represent different parts of the overall processing procedure. So it could be a different chunk of like amount that gets processed, a different time, just a different part of the overall processing procedure. Note also in our model G, we also have L, which is just the length of each edge. So how long it will take to move between different processing steps. We also have K pairs, ST, which is a sender and a receiver, and they have a certain amount, each pair has a certain amount of data that they need processed. So we're going to call this the demand. And we can note it as dem of I. We also in our model have a cost function, f of u, and that's the cost to process 1 unit of data. This function is non-decreasing and sub-additive, which means that processing 2 units of data together is going to be cheaper than processing those 2 units separately. An acceptable solution to this problem is a set of paths, pi to pk, where P1 to PK, where PI is a path from a sender to a receiver that processes the amount of data that they had demanded. For each solution, the cost per edge is CE, and that's the total amount of data that gets processed using that edge, so using that part of the processing procedure. The goal here is that we want to find a solution that minimizes the total cost over all edges. And by applying the FRT algorithm, we can provide an approximation that gives that solution within a factor of O of log n. And then just to finish, another application that I looked at was the approximate distance oracle, which is a compact storage data structure that answers pairwise distance queries. PTEs can be used to speed up this oracle construction. And then these ADOs can then be used in simulations, which would make them more efficient while still maintaining a level of accuracy in that approximation. Answering questions regarding pairwise distances is really important in modeling physical systems and the interaction of physical bodies with one another. like this galaxy merger simulation. So really quick, just to summarize, it's often more efficient to solve problems on trees instead of graphs. And so we can build alpha stretch PTEs that give approximate pairwise distances between nodes within a factor alpha of the actual distance. Then we looked at the FRT algorithm, which states that that stretch is O of log n, and that it's a tight bound, so we can't get any better. Then Blalock, Ga, and Sun in 2017 improved the runtime to O of m log n. And then finally, some applications include data processing and communication and the simulation of physical systems. Thank you so much for listening and for being here. If you have any questions, please send me an email. And thank you again to Dr. Valerie King for her supervision and her guidance. Great. Thank you so much. Bye.